We're going to start. We're going to start studying today and for quite a while the linear second-order differential equation with constant coefficients. So in standard form, it looks like there are various possible choices for the variable, unfortunately, so I hope that won't disturb you too much if I use one rather than another. I'm going to write it this way in standard form. I'll use y as the dependent variable. Your book uses little p and little q. I'll probably switch to that by next time, but for today I'd like to use the most neutral letters I can find for that won't interfere with anything else. So I'm going to call the constant coefficients respectively A, capital A, and capital B. I'm going to assume for today that the right-hand side is 0, so that means it's what we call homogeneous. The left-hand side must be in this form for it to be linear. It's second order because it involves the second derivative. These coefficients A and B are understood to be constant because I said it has constant coefficients. Of course, that's not the most general linear equation there could be. In general, it would be more general by making this a function of the independent variable x or t, whatever it's called. Similarly, this could be a function of the independent variable. And above all, the right-hand side can be a function of a variable rather than simply 0. In that case, the equation is called inhomogeneous, but it has a different physical meaning, and therefore it's customary to study that after this. You start with this. This is the case we start with, and then by the middle of next week, we'll be studying more general cases. But it's a good idea to start here. Your book starts with, in general, some theory of a general linear equation of second order and even higher order. I'm asking you to skip that for the time being. We'll come back to it next Wednesday, in 2 lectures, in other words. I think it's much better and essential for your problem set for you to get some experience with a simple type of equation, and then you'll understand the general theory, how it applies a lot better, I think. So let's get experience here. The downside of that is that I'm going to have to assume a couple of things about the solution to this equation, how it looks. I don't think that will upset you too much. So what I'm going to assume, and we'll justify it in a couple of lectures, that the general solution, that is, the solution involving arbitrary constants, looks like this. Y is the arbitrary constants occur in a certain special way. They're C1, Y1 plus C2, Y2. So these are 2 arbitrary constants corresponding to the fact that we're solving a second-order equation. In general, the number of arbitrary constants in the solution is the same as the order of the equation, because if it's a second-order equation, that means somehow or other it may be concealed, but you're going to have to integrate something twice to get the answer, and therefore there should be 2 arbitrary constants. That's very rough, but it sort of gives you the idea. Now, what are the y1 and y2? Well, as you can see, if these are arbitrary constants, if I take C2 to be 0 and C1 to be 1, that means that y1 must be a solution to the equation, and similarly y2. So where y1 and y2 are solutions. Now, what that shows you is how that the task of solving this equation is reduced, in some sense, to finding just two solutions of it somehow. By hook or crook, all we have to do is find two solutions, and then we'll have solved the equation, because the general solution is made up in this way by multiplying those two solutions by arbitrary constants and adding them. So the problem is, where do we get that solutions from? But first of all, or rather second or third of all, the initial conditions enter into the, I haven't given you any initial conditions here, but if you have them, and I'll illustrate them when I work problems, the initial conditions, well, the initial values are satisfied by choosing C1 and C2, are satisfied by choosing C1 and C2 properly. So in other words, if you have an initial value problem to solve, that will be taken care of by the way those constants C enter into the solution. Okay, without further ado, there is a standard example which I wish I had looked up the physics syllabus for the first semester. Did you study the spring mass dashpot system in 801? I'm embarrassed of having to ask you. You did? Raise your hand if you did. Okay, that means you all did. Well, just let me draw an instant picture to remind you. So this is a 2-second review of what you, I don't know how they draw the picture. Probably they don't even draw a picture at all. They have some elaborate system here, or the thing running back and forth. Well, in the math, we do that all virtually. So here's my system. That's some fixed thing. Here's a little spring. And there's a little car on a track here, I guess. So there's the mass. Some mass in the little car. And the motion is damped by what's called a dashpot. A dashpot is like the sort of thing that you see them in everyday life as door closers. They're the things up above that you never notice that prevent the door from slamming shut. So if you take one apart, it looks something like this. So that's the dashpot. It's a chamber with a piston. This is a piston moving in and out, and the air, compressing the air and releasing it, is what damps the motion of the thing. So this is a dashpot, it's usually called. And here's our mass in that little truck, and here's the spring. And then the equation which governs it is, let's call this x. I'm already going to change the dependent variable from y to x, but that's just for the sake of example, and because the track is horizontal, it seems more natural to call it x. There's some equilibrium position somewhere, let's say here. That's the position at which the mass wants to be if the spring is not pulling on it or pushing on it, and the dashpot is happy. I guess we better have a longer dashpot here. So this is the equilibrium position where nothing's happening. When you depart from that position, then the spring, if you go that way, the spring tries to pull the mass back. If it goes on this side, the spring tries to push the mass away. The dashpot, meanwhile, is doing its thing. And so the force on is the mx double prime. That's by Newton's law, the force comes from where? Well, there's the spring pushing and pulling on it. That force is opposed. If x gets to be beyond 0, then the spring tries to pull it back. If it gets to the left of 0, if x gets to be negative, then that spring force is pushing it this way, wants to get rid of it, get rid of the mass. So it should be minus kx, and this is from the spring. The fact that it's proportional to the amount by which x varies, that's called Hooke's law. Never mind that. This is a law. That's a law, Newton's law. Okay, Newton. Hook with an E, and the dashpot damping is proportional to the velocity. It's not doing anything if the mass is not moving, even if it's stretched way out of its equilibrium position. So it resists the velocity. If the thing is trying to go that way, the dashpot resists it. If it's trying to go this way, the dashpot resists that too. It's always opposed to the velocity, and so this is a dashpot damping. I don't know whose law this is. So it's the force coming from the dashpot. And when you write this out, the final result, therefore, is that it's mx double prime plus cx prime. It's important to see where the various terms are, plus kx equals 0. And now that's still not in standard form. To put it in standard form, you must divide through by the mass, and it will now read like this: plus k divided by m times x equals 0. And that's the equation governing the motion of the spring. I'm doing this because your problem set, problems 3 and 4, ask you to look at a little computer visual, which illustrate a lot of things. And I didn't see how to make, you can do it without this interpretation of spring mass dashpot, but I think thinking of it of these constants as this is the damping constant, and this is the spring, the constant which represents the force being exerted by the spring constant, as it's called, makes it much more vivid. So you'll notice that those problems are labeled Friday or Monday. Make it Friday. You can do them after today if you have a vaguest idea of what I'm talking about now. If not, go back and repeat 801. So all this was just an example, a typical model, but by far the most important simple model. Okay, now what I'd like to talk about is the solution. What is it I have to do to solve the equation? So to solve that equation that I outlined in orange on the board, the ODE, our task is to find two solutions. Now, don't make it too trivial. There's a condition that solution should be independent. All that means is that y2 should not be a constant multiple of y1. I mean, if you got y1, then 2 times y1 is not an acceptable value for this, because, as you can see, you really only got 1 there. You're not going to be able to make up a 2-parameter family. So the solutions have to be independent, which means, to repeat, that neither should be a constant multiple of the other. They should look different. That's an adequate explanation. Okay. Now, what's the basic method for finding those solutions? Well, it's what we're going to use all term long, essentially, studying equations of this type, even systems of this type, with constant coefficients. The basic method is to try y equals an exponential. Now, the only way you can fiddle with an exponential is in the constant that you put up on top. So we're going to try y equals e to the r t. So I'll use t as the deep. Notice you can't tell from that what I'm using is the deep independent variable, but this tells you I'm using t, and I'm switching back to using y as the dependent variable. So t is the independent variable. Why do I do that? The answer is because somebody thought of doing it, probably Euler, and it's been a tradition that's handed down for the last 300 or 400 years. Some things we just know. All right, so now if I do that, as you learned from the exam, it's very easy to differentiate exponentials. That's why people love them. It's also very easy to integrate exponentials, and half of you integrated instead of differentiating. But So we'll try this and see if we can pick R so that it's a solution. Okay, well, I'll plug in then. So I'll plug in, substitute in other words. And what do we get? Well, for y double prime, I get r squared e to the rt. That's y double prime, because each time you differentiate it, you put an extra power of r out in front, but otherwise do nothing. The next term will be r times, sorry, I forgot the constant, capital A times r e to the rt. And then there's the last term, b times y itself, which is b e to the rt. And that's supposed to be equal to 0. So I have to choose r so that this becomes equal to 0. Now you see, the e to the rt occurs as a factor in every term, and the e to the rt is never 0, and therefore you can divide it out, because it's always a positive number regardless of the value of t. So I can cancel that from each term, and what I've left with is the equation r squared plus ar plus b equals 0. We're trying to find values of r that satisfy that equation. And that, dear hearts, is why you learn to solve quadratic equations in high school. In order that at this moment you would be now ready to find how spring mass systems behave when they are damped. This is called the characteristic equation. The characteristic equation of the ODE, or of the system, of the spring mass system, which it's modeling. The characteristic equation of the system. Okay? Okay. Now, we solve it, but now from high school, you know, there are several cases. And each of those cases corresponds to a different behavior. And the cases depend upon what the roots look like. The possibilities are the roots could be real and distinct. That's the easiest case to handle. The roots might be a pair of complex conjugate numbers, but that's harder to handle, but we're ready to do it. And the third case, which is the one most in your problem set, is the most puzzling, when the roots are real and equal. And I'm going to talk about those three cases in that order. So the first case is the roots are real and unequal. If I tell you they're unequal, and I'll put down real to make that clear. Well, is by far the simplest case, because immediately one sees we have two roots, they're different, and therefore we get our two solutions immediately. So the solutions are, the general solution to the equation, I write down without further ado as y equals c1 e to the r1t plus c2 e to the r2t. There's our solution. Now, because that was so easy and we didn't have to do any work, I'd like to expand this case a little bit by using as an example of how you put in the initial conditions, how to put in the C. So let me work a specific numerical example, since we're not going to try to do this theoretically until next Wednesday. Let's just do a numerical example. So suppose I take the constants to be, the damping constant to be 4, and the spring constant, I'll take the mass to be 1, and the spring constant to be 3. So there's more damping here, the damping force here. You can't really talk that way since the units are different, but this number is bigger than that one. That seems clear at any rate. Okay, now, what's the characteristic equation? Look, now watch. Please do what I do. I've found in the past, even by the middle of the term, there are still students who feel that they must substitute y equals e to the rt and go through that whole little derivation to find that. You don't do that. It's a waste of time. I did it that you might not ever have to do it again, okay? Immediately write down the characteristic equation. That's not very hard. R squared plus 4R plus 3 equals 0. And if you can write down its roots immediately, splendid, but let's not assume that level of competence. So it's R plus 3 times R plus 1 equals 0. Okay, you factor it. This being 1803, a lot of the times the roots will be integers. When they're not, God forbid, you'll have to use the quadratic formula. Okay, but here the roots were integers. It's, after all, only the first example. So the solution, the general solution is y equals C1 e to the negative, notice the root is minus 3 and minus 1, minus 3t plus C2 e to the negative t. Now, suppose it's an initial value problem, so I gave you initial conditions. Suppose the initial conditions were that y of 0 were 1. So at the start, the mass has been moved over to the position 1 here. Well, we expect it then to start doing that. But this is fairly heavily damped. This is heavily damped. I'm going to assume that the mass starts at rest. So it's in a distended, the spring is distended, the mass is over here, but there's no motion at time 0 this way or that way. In other words, I'm not pushing it. I'm just releasing it and letting it do its thing after that. Okay, so y prime of 0, I'll assume, is 0. So it starts at rest, but in the extended position 1 unit to the right of the equilibrium position. Now, all you have to do is use these two conditions. Notice I have to have two conditions because there are two constants I have to find the value of. All right, so let's substitute. We're going to have to calculate the derivative, so why don't we do that right away? So this is minus 3c1 e to the minus 3t minus c2 e to the negative t. And now if I substitute in at 0, when t equals 0, what do I get? Well, the first equation, the left says that y of 0 should be 1, and the right says this is 1, that's 1, so it's c1 plus c2. That's the result of substituting t equals 0. How about substituting? What should I substitute in the second equation? Well, y prime of 0 is 0. So for the second equation, when I put in t equals 0, the left side is 0 according to that initial value, and the right side is negative 3c1 minus c2. You see what you end up with, therefore, is a pair of simultaneous linear equations. And this is why you learn to study linear pairs of simultaneous linear equations in high school. These are among the most important. Solving problems of this type are among the most important applications of that kind of algebra and this kind of algebra. All right, what's the answer, finally? Well, if I add the two of them, I get minus 2c1 equals 1. So c1 is equal to minus 1/2. And if c1 is minus 1/2, then c2 is minus 3c1, so it's c2 is 3/2. The final question is, what does that look like as a solution? Well, in general, these combinations of two exponentials aren't very easy to plot by yourself. That's one of the reasons you're being given this little visual which plots them for you. All you have to do is, as you'll see, set the damping constant, set the constants, set the initial conditions, and by magic the curve appears on the screen. And if you change either of the constants, the curve will change nicely right along with it. So the solution is The solution is y equals minus 1/2 e to the minus 3t plus 3/2 e to the negative t. How does it look? Well, I don't expect you to be able to plot that by yourself, but you can at least get started. It does have to satisfy the initial conditions. That means it should start at 1 and be its starting slope is 0. So it starts like that. These are both declining exponentials. This declines very rapidly, this somewhat more slowly. It does something like that. If this term were a lot more negative, that's the way that particular solution looks. How might other solutions look? I'll draw a few other possibilities. If the initial term, if, for example, the initial slope were quite negative, well, then it would have to start like this. Now, just your experience of physics or of the real world suggests that if I start the thing at 1, but give it a strongly negative push, it's going to go beyond the equilibrium position and then come back again. But because the damping is big, it's not going to be able to get through the equilibrium position a second time. It's going to look something like that. Or if I push it in that direction, the positive direction, then it starts off with a positive slope, but it loses its energy because the spring is pulling and it does something like that. So in other words, it might go down. Could it cross the equilibrium position, come back again and do that? No, that it cannot do. I was considering giving you a problem to prove that, but I thought I got tired of making out the problem set and decided I tortured you enough already, as you'll see. So anyway, these are the different possibilities for the way that can look. This case where it just returns in the long run is called the overdamped case. Overdamped. Now, there is another case when the thing oscillates back and forth. We would expect to get that case if the damping is very little or non-existent, then there's very little preventing the mass from going that, although we do expect, if there's any damping at all, we expect it ultimately to get nearer and nearer to the equilibrium position. Mathematically, what does that correspond to? Well, that's going to correspond to case 2, where the roots are complex. The roots are complex, and this is why, let's call the roots in that case, we know that the roots are of the form a plus or minus bi. There are 2 roots, and they're complex conjugate. All right, let's take one of them. What does it correspond to in terms of the exponential? Well, remember, the function of the r it's this r when we tried our exponential solution. So what we formally, this means we get a complex solution. The complex solution, y equals e to this, let's use one of them, let's say a plus bi times t. The question is, what do we do with that? We're not really interested. I don't know what a complex solution to that thing means. It doesn't have any meaning. What I want to know is how y behaves or how x behaves in that picture. And that better be a real function, because otherwise I don't know what to do with it. So we're looking for 2 real functions, the y1 and the y2, but in fact what we've got is 1 complex function. All right, now a theorem to the rescue. This I'm not going to save for Wednesday because it's so simple. So the theorem is that if you have a complex solution, u plus iv, so each of these is a function of time, u plus iv is a complex solution to a real differential equation with constant coefficients. Well, it doesn't have to have constant. It has to be linear. Let me just write it out, to y double prime plus a y prime plus by equals 0. Suppose you've got a complex solution to that equation. These are understood to be real numbers. They're the constant, the damping constant and the spring constant. Then conclusion is that u and v are real solutions. In other words, having found a complex solution, all you have to do is take its real and imaginary parts, and voila, you got your two solutions you were looking for the original equation. Now, that might seem like magic, but in fact, it's easy. It's so easy. It's the sort of theorem I can spend 1 minute proving for you now. What's the reason for it? Well, the main thing I want you to get out of this argument is to see that it absolutely depends upon these coefficients being real. You have to have a real differential equation for this to be true. Otherwise, it's certainly not. So the proof is, what does it mean to be a solution? It means when you plug in a u plus iv plus prime plus b times u plus iv, what am I supposed to get? 0. Well, now, separate these into the real and imaginary parts. What does it say? It says u double prime plus au prime plus bu. That's the real part of this expression when I expand it out. And I've got an imaginary part, too, which all has the coefficient I. So from here I get v double prime plus I times av prime plus I times bv. So this is the imaginary part. Now, here I have something with the real part plus the imaginary part. I times the imaginary part is 0. Well, the only way that can happen is if the real part is 0 and the imaginary part is separately 0. So the conclusion is that therefore this part must be 0 and therefore this part must be 0 because the two of them together make the complex number 0 plus 0i. Now, what does it mean for the real part to be 0? It means that u is a solution. The imaginary part 0 means v is a solution, and therefore, just what I said, u and v are solutions to the real equation. Where did I use the fact that a and b were real numbers and not complex numbers? In knowing that this is the real part, I had to know that a was a real number. If a were something like 1 plus I, I'd be screwed. I mean, because, then I couldn't say this was the real part anymore. So saying that's the real part and this is the imaginary part, I was using the fact that these two numbers, constants, were real constants. Very important. Well, so then how do I solve so what is the case 2 solution? Well, what are the real and imaginary parts of a plus bit? Well, y equals e to the a plus at plus ibt. Okay, you've had experience, you know how to do this now. That's e to the at times, well, the real part is, let's write it this way. The real part is e to the at times cosine bt. Notice how the a and b enter into the expression. That's the real part. And the imaginary part is e to the at times the sine of bt. And therefore the solution, both of these must therefore be solutions to the equation, and therefore the general solution to the ODE is y equals, now you've got to put in the arbitrary constants. It's a nice thing to do to factor out the e to the at. It makes it look a little better. And so the constants are c1 cosine bt and c2 sine bt. Yeah, but what does that look like? Well, you know that too. This is an exponential which controls the amplitude, but this guy, which is the combination of two sinusoidal oscillations, with different amplitudes, but with the same frequency. The B's are the same in both of them, and therefore this is itself a purely sinusoidal oscillation. So in other words, I don't have room to write it, but it's equal to, you know. It's a good example of where you would use that trigonometric identity I spent time on before the exam. Okay, let's work a quick example just to see how this works out. Well, let's get rid of this. Okay, let's now make the damping. Since this is showing oscillations, it must correspond to the case where the damping is less strong compared with the spring constant. A stiff spring, one that pulls with a hard force, is going to make that thing go back and forth, particularly if the damping is weak. So let's use almost the same equation as I've just concealed. But do you remember I used 4 here? Okay, here before we used 3, and we got this solutions that look like that. Now we'll give it a little more energy by putting some moxie in the spring, so now it's 5y. The spring is pulling a little harder. Bigger force, a stiffer spring. Okay, the characteristic equation is now going to be r squared plus 4r plus 5 is equal to 0. And therefore, if I solve for r, I'm not going to bother trying to factor this because I prepared for this lecture and I know, quadratic formula time. Minus 4 plus or minus the square root of b squared 16 minus 4 times 5. 16 minus 20 is negative 4 all over 2, and therefore that makes negative 2 plus or minus, this makes simply I. 2I divided by 2, which is I. So the exponential solution is e to the negative 2. You don't have to write this in. From here you can get the thing directly. T, let's use the one with a plus sign. And that's going to give, as the real solutions, e to the negative 2 times cosine t and e to the negative 2t times the sine of t. And therefore the solution is going to be y equals e to the negative 2t times c1 cosine t plus c2 sine t. If you want to put initial conditions, you can put them in the same way I did them before. Here are some, suppose we use the same initial conditions. Y of 0 equals 1, and y prime of 0 equals 1, equals 0, let's say. It's not, blah, 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 blah. 0, yeah. Okay, I'd like to take time to actually do the calculation, but there's nothing new in it. I'd have to calculate the derivative here, and then I would blah, 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 substitute in, solve equations. And when you do all that, just as before, the answer that you get is y equals e to the negative 2t. So the one which, to choose the constants c1 and c2 by solving linear equations, and the answer is cosine t. So c1 turns out to be 1, and c2 turns out to be 2, I hope. Okay, I want to know, but what does that look like? Well, use that trigonometric identity. What's the e to the negative 2t is just a real factor which is going to reproduce itself. The question is, what does cosine t plus 2 sine t look like? What's its amplitude as a pure oscillation? It's the square root of 1 plus 2 squared. Remember, it depends on looking at that little triangle, which is 1, 2. This is a different scale than that. And here is the square root of 5, right? And here is phi, the phase lag. So it's equal to the square root of 5. So it's square root of 5 times e to the negative 2t, and the stuff inside is the cosine of, the frequency is 1, circular frequency is 1, so it's t minus phi, where phi is this angle. How big is that? 1 and 2. Well, if this were the square root of 3, which is a little less than 2, it would be 60 degrees, so this must be 70 degrees. So phi is 70 degrees, plus or minus 10, 5, let's say. So it looks like a slightly delayed cosine curve, but the amplitude is falling. Looks something like, so it has to start. So if I draw here is 1, here is, let's say, the square root of 5 up about here, then the square root of 5 times e to the negative 2t looks maybe something like this. So that's square root of 5 e to the negative 2t. How about this is cosine t, but shoved over by not quite pi over 2. It starts at 1 and with slope 0. So the solution starts like this. It has to be guided in its amplitude by this function out there, and in between it's the cosine curve, but it's moved over. So if this is pi over 2, the first time it crosses is 72 degrees to the right of that. So if this is pi over 2, it's pi over 2 plus 70 degrees, where it crosses. So it must be doing something like this. And now on the other side, it's got to stay within the same amplitude. So it must be doing something like this. Okay, that gives us to, if this is the underdamped case, because if you're trying to do this with a swinging door, it means the door's going to be swinging back and forth. Or our little mass, now hidden, but you can see it behind that board, is going to be doing this. But it never stops, never stops. It does in real life, but not in theoretical life. So this is the underdamped case. All right, so it's like Goldilocks and the Three Bears, you know, that's too hot and this is too cold. What is the thing which is just right? Well, that's the thing you're going to study on the problem set. So just right is critically damped. It's called critically damped. It's what people aim for in trying to damp motion that they don't want. Now, what's critically damped? It must be the case just in between these two. Neither complex nor the roots different. It's the case of two equal roots. So r squared plus ar plus b equals 0 has two equal roots. Now, that's a very special equation. Suppose we call the root, since all of these, notice these roots in this physical case, the roots always turn out to be negative numbers or to have a negative real part. I'm going to call the root a. So r equals negative a, the root. A is understood to be a positive number. I want that root to be really negative. Then the equation looks like, the characteristic equation is going to be r plus a, right, if the root is negative a, squared because it's a double root. And that means the equation is of the form r squared plus 2 times a r plus a squared equals 0. In other words, the ODE looked like this. The ODE looked like y double prime plus 2ay prime plus, in other words, the damping and the spring constant were related in this special way. That for a given value of the spring constant, there was exactly one value of the damping which produced this in-between case. Now, what's the problem connected with it? Well, the problem, unfortunately, is staring us in the face when we want to solve it. The problem is that we have a solution, but it is y equals e to the minus at. I don't have another root to get another solution with. And the question is, where do I get that other solution from? Now, there are 3 ways to get it. Well, there are 4 ways to get it. You look it up in Euler. That's the 4th way. That's the real way to do it. But I've given you one way as problem number 1 on the problem set. I've given you another way as problem number 2 on the problem set. And the 3rd way, you'll have to wait for about a week and a half, and I'll give you a 3rd way too. By that time, you won't want to see any more ways. But I'd like to introduce you to the way on the problem set, and it is this, that if you know one solution, it's called, if you know one solution to an equation which looks like a linear equation. In fact, the p's can be functions of t. They don't have to be constant, so I'll use the book's notation, p with p's and q's. Y prime plus qy equals 0. If you know one solution, there's an absolute iron guarantee, and you'll know that it's true because I'm asking you to prove it for yourself. There's another of the form having this as a factor. One solution, y1, let's call it. Y equals y1u is another solution, and you will be able to find u, I swear. Now, let's, in the remaining a couple of minutes, carry that out just for this case, because I want you to see how to arrange the work nicely, and I want you to arrange your work when you do the problem sets in the same way. So the way to do it is, the solution we know is e to the minus at. So we're going to look for a solution to this differential equation. That's the differential equation. And the solution we're going to look for is of the form e to the negative at times u. Now, you're going to have to make a calculation like this several times in the course of the term, so that do it this way. Y prime equals, differentiate, minus a e to the minus at u plus e to the minus at u prime. And then differentiate again. The answer will be a squared, you differentiate this, a squared e to the negative at. I'll have to do this a little fast, but the next term will be, minus, so this times u prime, and from this you're going to get another minus. So combining what you get from here and here, you're going to get minus 2a e to the minus at u prime. And then there's a final term which comes from this e to the minus at u double prime. 2 of these, because a piece here and a piece here combined to make that. And now, to plug into the equation, you multiply this by 1. In other words, you don't do anything to it. You multiply this line by 2a, and you multiply that line by a squared, and you add them. On the left-hand side, I get 0. What do I get on the right? Notice how I've arranged the work so it adds nicely. This is a squared times this, plus 2a times that, plus 1 times that makes 0. 2a times this, plus 1 times this makes 0. All that survives is e to the at u double prime, and therefore e to the minus at u double prime is equal to 0. So please tell me, what's u double prime? It's 0. So please tell me, what's u? It's c1t plus c2. Now, that gives me a whole family of solutions. Just t would be enough, because all I'm doing is looking for one solution that's different from e to the minus at. And that solution, therefore, is y equals e to the minus at times t. And there's my second solution. So this is the solution of the critically damped case, and you're going to use it in 3 or 4 of the different problems on the problem set. But I think you can do with virtually the whole problem set except for the last problem now.